You ever stop and think about how a super simple, everyday tool can basically give you superhuman strength? I mean, we're surrounded by all this complex tech, but honestly, some of the most powerful inventions in history are the simplest. Today, we're going to break one of them down: the lever. So, you've probably heard this famous quote from the ancient Greek scientist Archimedes: "Give me a lever and a place to stand, and I will move the world." Seriously? Was this guy just exaggerating? Or did he tap into some fundamental secret of physics that lets us multiply our own power like crazy? Okay, so let's get into it. To really understand what Archimedes was talking about, we have to peel back the layers of myth and just look at the straight-up science. What exactly is a lever, and how does all this supposed magic actually work? At its core, a lever is incredibly, almost ridiculously simple. It's just a rigid bar, think a stick, a plank, whatever, that pivots around a fixed point. And its whole job, its entire reason for being, is to make a task easier to do. That's it. A bar, a pivot point, and a job. Now, for that simple bar to actually do anything, you need three key ingredients working together. First, you've got the fulcrum. That's just the fancy word for the fixed pivot point. Then you have the effort, that's the force that we put in. And finally, you've got the resistance, which is the force from whatever it is we're trying to move. And, a simple pair of scissors is the perfect everyday example of this. The little screw right in the middle, that's your fulcrum, the pivot. Your hand squeezing the handles, that's the effort. And the force the blades create to actually cut through paper, that's the resistance. Fulcrum, effort, resistance. All right there, one simple tool. But here's where it gets interesting. The order of those three things, the fulcrum, the effort, and the resistance, it matters a lot. See, depending on how you arrange them, you get three totally different classes of levers, and each one is useful for different things. And what's so cool is that this basically gives you the blueprint for tons of tools we use every single day. For a class 1 lever, the fulcrum is sandwiched in the middle. Think of a seesaw or our scissors example. In a class 2, the resistance is in the middle, like when you're using a bottle opener or a nutcracker. And with a class 3, the effort is in the middle. You see that with things like a broom or a pair of tweezers. So you've got all these different arrangements, right? But here's the thing. No matter which class it is, the goal is always the same. Levers are designed to give us what's called a mechanical advantage, to basically hack forces to make our work easier. But how can we be sure this actually works in the real world? And that question, it really gets to the heart of how science works. It's one thing to understand an idea on paper, but it's a whole other thing to prove it in practice. This is where we bridge the gap between theoretical and experimental physics. See, you've got these two sides of the same coin. On one hand, there's theoretical physics. It's all about the principles, the equations. It's the part that predicts how something should work. But then you have experimental physics, which is all about getting your hands dirty with observation and real-world tests to see if those predictions actually check out. And honestly, you can't have one without the other. So, enough with the theory. Let's put this lever idea to the test with a super simple experiment you could literally build in your living room right now. This is where we find out if the physics we've been talking about really holds up. Okay, the setup is dead simple. Grab a broom handle, that's our lever. Now rest it on the back of a chair, that's our fulcrum. On one side, hang a bag with some heavyish stuff in it, that's our resistance. And your hand pushing down on the other side, that's the effort. Simple, right? All right, here's the million-dollar question for our little experiment. What do you think happens when you slide that bag, the resistance, closer to the chair, our fulcrum? Do you have to push harder with your hand, or does it actually get easier to lift? And the answer our experiment gives us is this: the farther your hand is from the chair, the farther your effort is from the fulcrum, the less force you need to lift that heavy bag. You're increasing the distance on your end, and that magically decreases the effort you need to put in. And there it is. The experiment confirms the theory, just like that. This right here is the secret of the lever. It gives us that mechanical advantage by letting us trade distance for force. You push down a long way with just a little bit of force, so you can lift a heavy object just a short way. It's a trade-off. Now here's the really cool part. Once this clicks for you, you're going to start seeing it absolutely everywhere. Physics isn't just locked away in some lab or textbook. It's all around us, usually hiding in plain sight. I mean, really think about it. The scissors we talked about, a pair of pliers, can openers, brooms, the stapler on your desk, even something as small as nail clippers. Your home is basically a museum of these brilliant little machines. Every single one is a lever,
perfectly designed to multiply your force. So let's bring it all the way back to the beginning. It turns out Archimedes wasn't just bragging. He was right. With a long enough lever and a solid place to stand, the physics totally checks out. You really could move the world. That power is all around us, just waiting. So now that you know the secret, what world will you move?